So we're able to write a function as a power series. Okay, so this is part 2 of the power series. So this is about power series and functions. Basically, some functions can be written as a power series, and a function is defined as a power series, and the domain of the function is the interval of convergence. So we showed how to do that on the last video. So if the radius of convergence is greater than 0, then the neat thing about this would be that the function would be differentiable and integrable on the interval centered at A. And we go R, the radius is R, so we go R to the right and left. And we find these 2 points, A plus R and A minus R. So I'm going to show you, we're going to be needing this skill in the upcoming sections. We will be needing to take the derivative of a series and also the integral of a series. So let's see what that looks like. And my first word of caution is to be careful with the indices. So we're going to take the derivative of a series. And so basically, I mean, this is representing all the terms, so we can do it in general. And it'll be, you just use the power rule here, n times a to the n, x minus a to the n minus 1. And now what we have to be careful with when we take the derivative is the first index. We don't want to start it at n equals 0 because then we'll have a negative exponent. And we know with polynomial, we don't have that. So it makes sense. We will be starting with a constant. The constant will be, the power will be 0. So if we start at 1, then we can see 1 minus 0 is 0, and there's our constant. So again, this makes our first term constant. That's what we want. Okay, so now let's take the integral. Of the series. And just like before, we will integrate each term and we add 1 to the power and then we divide by that power. So here actually our index stays the same. You can see our constant term here starts with the constant. We'll now have, we'll now have an x to it. And let's look at this also. Here, the first term, when that's 0, the exponent is 0, is a to the n, that's our constant. And here, now our first term, I plug in 0, and up here, it's a to the n times x, because that'll be 0. Well, x minus a, actually. So we have, if we have functions that are infinitely differentiable, then they can be represented by a Taylor or Mclaren series, or just a power series in general. So let's write that out. So you plug in 0, you get f of a. And then we have the Mclaren series. So basically the difference is the Taylor series are centered around A, and you can see it's x minus a. It's shifted a to the right, you can see that. So it shifted about a, or centered around A. The Mclaren series is a Taylor series where a is equal to 0. It's centered around the 0. So we write that. So that a is just 0. Again, this is just, both of these are just constants. And we can write that out if we want to. And the pattern continues. So I'm going to show you how to do this. We're going to create a Mclaren series, so about 0 for f of x is equal to e to the x. This is one of the easier ones to do. So let's remember our function, we're going to rewrite as an infinite polynomial, and there's the formula to do it. So we need to basically find first fn of 0. So let's find fn of x first and then plug in 0. This one's pretty simple because the derivative's the same thing. So we can see f, the pattern. The nth derivative is going to be the same. But what we want is 0. So f of 0 equals e to the 0. All of them are, in fact, which is 1. F prime of 0, which is 1. Fn of 0 equals e to the 0, which is 1 also. So they're all 0. This part in it right here is 1. And so we just write out the formula. So e to the x is our function. Our f of x is our e to the x, which is the sum of n equals 0. And this part we found to be 1. Is 1 over n factorial x to the n, which is just x to the n over n factorial. And we can write this out. Plug in 0. We get x to the 0 all over 0 factorial, which is 1. X to the 1 over 1 factorial is just x. X squared all over 2 factorial. And we can see that pattern continues. Pretty simple series. This interval of convergence, by the way, is all real numbers. So what if, now that I know what the series of e to the x looks like, what if I want to find e to the x squared? So we have e to the x, it's right here. And what we want to do is we want to replace x with x squared. So everywhere we see an x, all the x's, and it works if you put an x squared here and then write this one out, simplify it, and then write it out, or we can replace all the x's. That x will be x squared. This second x will be x squared. squared all over 2 factorial. This will be x squared to the third all over 3 factorial. And to simplify that, we can simplify both of them. This is power to power, 2 times n to the n factorial. This is x to the fourth. And it looks like we have this is the same. So the next thing I'm going to do, and this is very popular, we're going to need this skill very badly in the next coming up sections. This is manipulation of the series terms. We want to basically learn how to combine the series into one series. So let's look at an example. Okay, so our goal is to write as a single power series. So the first thing we want to look at, I mean, you can think of these as terms. If we're adding powers of a function, they have to be the same power, okay? They also have to have the same index. So let's write that out. The question is, what power of x is at the start of each series? So the goal is okay, so they need to be the same power in order to add, and the index must also be the same. So for this one, I'm just going to copy it again because I'm going to work on it. Let's go ahead and figure out where we're starting. So we plug in our first, n equals 3, our first term. And for now, I only care about the power. So it's x to the 3 minus 2. And this one, I plug in n equals 1 here, and we get x to the 1. Are they equal? That's the question. So that's x to the 1 equals x to the 1. So I'm going to check that off. Yes, they're the same. We'll learn what to do later if they're not. So what's not the same are their indexes, okay? We are going to have to use substitution. Again, if they're going to be the same index, if we can get them to be the same, look like the same power, then it's going to have the same index. So what we're going to do is I want both of these to be the k power. So what we're going to do is on this one, we're going to use, we're going to use the substitution. We're going to let k equal to n minus 2. This is separately. And over here, we'll let k equal to n. Okay? So we're just going to change them both to k's. And we both want them to be the same k power, because what will happen here is if we're using k equals n, if we're using this substitution, then if n equals 3, we get k equals 3 minus 2, which is 1. So this index is k equals 1. But we also have to change all of these n's. So this n becomes k plus 2. That second n is k plus 2 minus 1. C, the subindex changes too. Now this one is pretty simple. We just replace k with n. And now, if you look, they have the same index, they have the same power. We're now ready to add them. So we're going to add this. I'm just adding all of this. We do have the power in common, so we can write the power on the outside, factor it out basically, and then add the stuff before it. And like I mentioned before, we did factor this out and put it at the end. Let's do another one. Okay, so again, we always have to check powers first. I always plug in the first. So we're going to check powers. Basically, just plug in the first term. We're going to check the first term. I plug in n equals 1, and I get x to the 0. And this one, that's that one. Plug in n equals 0, and I get x to the 1. So they are not the same. Those are not equal. They were the same in the last problem. So what we have to do is, I think the easier, there's more than one way to handle it, but I think the easier way is to peel off one of them. And so what we can do is we obviously can take away x to the 0, and then our next term will be x to the 1. Okay, so we're going to take off n equals 1 and write it on the outside. And then we could add the two series. So this one here is the one we need to work with. And we're just going to take off, for n equals 1, we're going to write the term. So that's 2 times 1 times x to the 0. Plus, for n equals 2, I'll just write the series. That's my next one. Okay. That's for n equals 2. So, you can see what I'm doing. For n equals 1, I plug in 1 here and 1 here, 1 there and 1 there. I'll get 0. And then my next for n equals 2 and 3 and 4 all the way to infinity, I represent it as an infinite sum. Okay? So again, we just peeled off basically the first term. There's the first term, and then the second term and all the other terms are still there. And now we can check. You want to check plugging in n equals 2. We just want to worry about this. It's n to the 2 minus 1, which is x to the 1, which is now the same power. Okay? Next, we need to make sure they're the same power. So now we want x to the k. So we'll just do exactly what we did last time. Let me finish writing this. My second one, then I'm just going to copy that down. So basically, I'm going to call this k, and I'm going to call that k. And so our substitution here, and we have this is just 2 in the front. So we're going to that was just scratch work, checking the powers. We're going to let k equals n minus 1, and also it's the same thing as saying n equals k plus 1. So we need both of them. I like to write them both out personally. We need to change the index, and we need to change the ends. So this is my index at n equals 2. If I plug in 2 here, k equals 1. So again, I'm just plugging in 2 here, minus 1. 2 minus 1 is 1. K equals 1 to start. And then 2, this n is k plus 1. And we already know that's x to the k. That's why we chose that. So this is a different substitution. This substitution is k equals n plus 1. It's right there. I want my power to be x. I like to solve for n. N is k minus 1, subtracting it over. I do need to plug in n equals 0 here, so I get k equals 1. The 6 is there, the c, and that's why I solved for n. The c to the n is c to the k minus 1, and replaced with k minus 1. And that'll be x to the k. Now I gotta actually combine these two, but now we see my index is the same and my power is the same. Pretty nifty, huh? So I'm adding this and this, factor out the x to the k. So I combine them, and that's my answer.